Welcome back. Our last video introduced the idea of the JuMP package in Julia and some of the ways in which it can be useful to us as applied econometrics researchers in economics. And in this video, I wanted to go over how JuMP could be useful specifically in easily imposing constraints on our objective functions. And imposing constraints is actually quite useful because some aspects of a structural model need a little more structure than others, and imposing constraints is a form of adding structure to the problem. And this can help with numerical instability issues or imposing theoretical results that you want to definitely hold in your situation. So the plan for this video is to go through the theory of constrained optimization and then go through a coding demonstration where we do some tried and true simple econometrics estimation in Optim and JuMP, and then show how JuMP can be very useful for imposing constraints. As I was saying, constraints in optimization can be useful for a number of reasons. For numerical stability, an example of this would be if the optimizer tries to guess a negative value for the variance of a distribution, that's going to crash because that's undefined. You can also make results consistent with economic theory. So you would want to, for example, impose that the discount factor has to be in the unit interval. Anything outside of that is undefined and would presumably cause the rest of your model results to be unbelievable. Or it can be useful to shut down channels of your model. For example, if I set beta equal to 0, where beta is the discount factor, then I know that my dynamic problem is no longer an issue. I'm estimating a static model. Constraints can also be useful for solving equilibrium models through a tool or a process, known as MPEC or MPEC that we'll get into in a later video of this mini-series. What are the basics of constrained optimization? Well, we need to go back to our intermediate or advanced microeconomic theory course where we learned about a Lagrangian. So we want to maximize or minimize some objective function f of x subject to some constraints. So we write down the Lagrangian like so, and in our case, the objective function is the likelihood function or the minimum distance objective function, and the x's are the parameters, the betas, the coefficients that we're trying to estimate. And we can take the first derivative to get the first order conditions, but we also have to satisfy the second order conditions and the Kuhn-Tucker conditions. And the second order conditions are going to involve what's called the bordered Hessian. So hopefully this is ringing a bell to you if you've taken a class in economics that has used these constrained optimization techniques. All we're doing is applying this with the computer. We're not doing the analytical calculus by hand. So how do we use JuMP, and how does that relate to the Lagrangian that we just talked about? Well, let's just go through a simple example and introduce how to use JuMP. So there's 4 basic components to any JuMP model. It's going to require you to specify an optimizer, variables to optimize, constraints, if any. It's okay to not have any constraints, and the objective function that's going to have the constraints put on it. And just as a comparison, this is not that different than what goes into Optim.jl, except the constraints part. So now that we have this, let's do JuMP on an unconstrained problem just to see how it works, and then we can talk a little bit more about constraints. All right, I've got my VS Code loaded up with a Julia script. I need to install the JuMP package, the Ipopt package, and the line searches package, and the mathopt interface package. These are the ones we've used in the past. Maybe sparse arrays you might not have that could be useful. And I'm going to read in a CSV with some wage data, just very typical application for this channel at least. And we are going to estimate the parameters of a linear regression model using the normal MLE. So we assume that the errors in the regression model are normally distributed, and then that allows us to specify a likelihood function that we can then maximize. And that likelihood function is just the normal PDF. Take the log of it, add it up over all the observations in my data, then take the negative since we want to minimize the negative log likelihood function. And once you distribute the log through, it actually has this nice linear function. It looks a lot like the least squares objective function. So this is just regular Optim.jl, and we can do the optimization in this chunk of the code, we can get the Hessian, and then from there, we could get the standard errors. So that's all well and good. And then, how would we do this in JuMP? Well, JuMP, we have to write a helper function to work with the Hessian to get the standard errors. I don't want to go through that in this video. And then we specify the likelihood function. So we first declare a model and that we're using the Ipopt optimizer. Then we specify our variables, which are the betas and the root mean squared error, and we can give it starting values to start from. And then we specify our objective, and here is nice, we can specify whether it's a maximization or a minimization, and we can just specify that that same sum of the log of the normal PDF taken over our whole sample. And the only difference with JuMP is that you have to explicitly specify everything as a scalar. There's no matrix multiplication allowed. And so we have to express these using comprehensions or loops. And then we tell it to optimize. We get the coefficients from the optimizer, and then we can also calculate the Hessian at the estimated values to get the standard errors. And the Hessian is just going to be the square root of the diagonal of the inverse of the negative Hessian if we're maximizing. All right, so I'm going to put a breakpoint in the code, and then I'm just going to let this run. And we've got our results. I've maximized the results window. Note that it could take a minute or so to precompile some of the packages that we've loaded, but we've got our OLS estimates using the matrix algebra formula and using Optim.jl on the maximum likelihood function. And then we've done the same thing with JuMP. We get exactly the same coefficients with JuMP as we did with Optim.jl. And then I had it throw an error just to stop the execution, given what else I had in the code. So going back to the slides, that's a little bit how JuMP works. And then what are some limitations or considerations to keep in mind when you're using JuMP? Well, as I mentioned in the coding walkthrough, you can't vectorize the objective function. Everything has to be a scalar. And you can't use objects like log PDF from the distributions.jl package. And as I demonstrated, we had to have a helper function to do the Hessian that was a little bit ugly in order to get the right standard errors. However, the nice thing is that it's very simple to add a constraint to JuMP. And the other thing to keep in mind is that once you do impose that constraint, then it's going to get the Hessian of the Lagrangian instead of the Hessian of the unconstrained likelihood function. And so that's going to potentially throw things off. So you're going to have to do some additional processing if you want to impose constraints and get the right standard errors back. So let's go back to the code and do a quick innovation where we impose a constraint on our objective function in JuMP and then see what that gets us. So I'm going to go in the code. I'm going to delete that breakpoint that I had, and I'm going to have the same function that I had before for JuMP. The only difference is that I'm adding a couple of constraints here. So I'm adding that beta 2 equals 0.16 and that beta 4 is 1 plus 2 times beta 3. Everything else is the same, and then I can call that function and print the results. And then I'll just put a breakpoint in here and hit play. All right, that finished. We're getting very similar results as before. We took this second coefficient and we're setting it equal to 0.16. That's going to cause the other coefficients to adjust accordingly to match that constraint. And we also imposed another constraint on beta 3 and beta 4. And one thing you'll notice with the standard errors is that they're complex numbers. So that must mean somewhere we took the inverse of a matrix that was not positive definite, which caused the components of that inverse to be complex instead of real valued. And that is probably some of the complications with the Hessian on the constrained likelihood function that I just mentioned. And if we have a coefficient set to a fixed value, it should not have a standard error associated with it. And so that's going to cause a little bit of a red flag for us that we need to review later. But this worked. All we had to do was add 2 lines of code. Everything ran quickly and nicely. The constrained likelihood function is lower than the unconstrained one, as we would predict. So everything looks fine there. So that was a little bit about how to use JuMP and constraints and how to do constrained optimization, as well as how to do very simple regression models in JuMP. And again, the goal with starting with a contrived simple example is to build up the intuition on a known problem that we can check and that we know the answer to. And then from there, we can start to depart into more interesting problems. In the next video, I'm going to illustrate how we can impose constraints in a basic likelihood function in Optim.jl, and then also talk about how to supply an analytical gradient to Optim.jl as a way of speeding up the optimization.